Voilà, donc la première partie de l'exposé sera en français parce qu'elle traitera du mémoire. Et c'est plus commode de parler en français sur des citations en français. La partie plus technique, hein, plus contemporaine, sera en anglais. Donc j'ai voulu parler d'un traité de Lagrange de mécanique des fluides. Et donc je ne suis pas historien, j'ai voulu insister sur les retombées, les conséquences, les idées qu'il y a dans le mémoire, et de montrer qu'elles sont encore très actuelles et que beaucoup de recherches en fait, actuelles sur la théorie des vagues remontent en fait aux idées de Lagrange. Donc il y aura une partie sur le traité lui-même, je ne serai pas exhaustif, je vais faire quelques zooms en fait sur des parties précises du traité, et puis je ferai une partie peut-être un peu plus longue sur les développements récents en fait, de la théorie, enfin récents. Voilà. Tout commence en fait avec Euler, donc dans un mémoire de 1755, où Euler établit les équations d'Euler, donc des fluides parfaits incompressibles. Donc j'ai écrit ici en langage moderne pour aller un peu plus vite. Donc ces équations sont basées sur deux lois de conservation, la conservation de la masse, hein, l'équation numéro 1, donc qui pour un fluide incompressible se réduit à la condition de divergence de la vitesse. Donc V c'est le champ des vitesses et ρ la densité du fluide, donc ρ est constante ici, et la loi de Newton, donc F égale m gamma. Donc la partie gauche de l'équation 3 c'est l'accélération, et à droite ce sont les forces sur le fluide, donc qui sont de deux types. Il y a la pression, donc le terme 1-1 sur ρ gradient P, et la gravité G. Donc dans ce modèle, on néglige complètement les forces de viscosité, donc qui seront introduites par Navier plus tard, et toute espèce de rhéologie du fluide, polymère bien sûr, qui ne sont pas décrites ici. Donc c'est le modèle le plus simple en fait de fluide. Que Euler a établi en 1755. Donc c'est un peu le point de départ en fait du mémoire de Lagrange. Donc ce mémoire s'appelle Mémoires sur la théorie du mouvement des fluides. Et il est paru donc en français à Berlin en 1780-81. Donc dans l'introduction en fait, donc Lagrange décrit un peu ses motivations. Donc ces motivations, essentiellement, si je comprends bien, c'est que, en gros, les équations des fluides, donc comme écrites par... D'ailleurs, Lagrange ne parle jamais d'Euler dans le mémoire, il cite d'Alembert et Bernoulli, mais jamais Euler. Donc ces équations sont très générales, mais en fait, on ne peut pas en faire grand-chose. Hein, donc il faut essayer d'aller voir un peu plus loin pour voir qu'est-ce qu'on peut en faire, à la fois mathématiquement et du point de vue physique. Voilà, donc depuis que M. d'Alembert a réduit à des équations analytiques les vraies lois du mouvement des fluides, cette manière est devenue l'objet d'un grand nombre de recherches qui se trouvent répandues dans les opuscules de M. d'Alembert et dans les recueils de cette académie, celle de Berlin, celle de Pétersbourg. La théorie générale a été beaucoup perfectionnée dans ces différentes recherches, mais il n'en est pas de même de la partie de cette théorie qui concerne la manière de l'appliquer aux questions particulières. M. d'Alembert paraît même porté à croire que cette application est impossible dans la plupart des cas, surtout lorsqu'il s'agit du mouvement des fluides qui coulent dans des vases. Je pense qu'il fait allusion à ce qu'on appelle le paradoxe d'Alembert, dont je ne parlerai pas ici. Donc voilà, donc je continue la citation donc, de Lagrange. Donc après avoir soigneusement étudié tout ce qui a déjà été écrit sur la théorie rigoureuse du mouvement des fluides, je me suis appliqué à lever, ou du moins à diminuer les difficultés qui ont retardé les progrès de cette théorie et ont obligé les géomètres à se contenter pour la solution des problèmes les plus simples de méthodes indirectes ou fondées sur des suppositions précaires. C'est ce qui a occasionné les recherches dont je vais donner le résultat dans ce mémoire. Donc le mémoire en fait comporte deux sections. La première section donc, s'appelle « Considérations générales sur les équations fondamentales du mouvement des fluides », où essentiellement donc Lagrange établit les équations générales du mouvement des fluides. D'ailleurs, fluide incompressible et compressible, donc, contrairement aux équations d'Euler qui traitaient uniquement des écoulements des fluides incompressibles. Et dans la deuxième partie, donc du mouvement des fluides pesants et homogènes dans des vases ou dans des canaux de figure quelconque, il s'applique à appliquer la théorie à des situations, disons, concrètes. Et moi, ce qui m'intéressera, c'est la deuxième, donc la seconde partie divisée en deux sous-sections. Et ce qui m'intéressera ici, c'est la deuxième sous-section qui traite du mouvement d'un fluide contenu dans un canal peu profond et presque horizontal, et en particulier du mouvement des ondes, dont c'est exactement le sujet de ce qu'on appelle maintenant la théorie des water waves ou des ondes hydrodynamiques si on parle français. Voilà, donc je vais rapidement d'abord montrer un peu les notations qu'utilisait Lagrange. Donc là, la première, il y a une faute dans la première transparent. Ça, c'est l'équation de la conservation de la masse, l'équation dont d ρ sur dt plus divergente de ρu égale 0. Donc là, la densité est notée delta ici par Lagrange. Et là, ce que j'ai fait, j'ai copié en fait la deuxième équation, l'équation quand le fluide est incompressible. Donc en fait, il faut lire d sur dx de delta p, d sur dy de delta q, etc. Donc ça, c'est ce qui se passe quand on suppose que la densité est constante, dont on déduit les conditions d'incompressibilité. Voilà, donc c'est la première équation fondamentale, la théorie du mouvement des fluides, et comme elle est relative à la densité du fluide, elle peut être nommée en général l'équation de la densité. Donc c'est l'équation que j'avais écrite avant, le premier transparent sur l'air. Donc ensuite, essentiellement, il écrit donc les équations. Bon là, en fait, je pense que j'ai pas lu le traité de Euler, mais il est en train de réécrire en fait la dérivation des équations de mécanique du fluide. Donc il écrit l'équation de Newton, hein, d'accord. Et donc là, il fait ce passage fait allusion en fait, au fait qu'il considère aussi des fluides compressibles. Donc, dans le cas, il y a une loi d'état. Donc, il précise en fait la loi d'état qui relie la pression et la densité. Donc, ce qui n'était pas dans l'air apparemment. Donc, ça, c'est quelque chose qui est un peu orthogonal à mon exposé parce que je ne considérais que les fluides incompressibles. Mais c'est juste pour dire que il considère donc ce qu'il appelle les fluides compressibles et élastiques. D'accord. Donc, ils comprennent les fluides compressibles en particulier, mais dont je ne parlerai pas. Alors donc, la deuxième chose aussi, bien sûr, laquelle on est très habitué maintenant, c'est qu'il ne suffit pas d'écrire les équations donc aux dérivées partielles, aux différences partielles, comme Lagrange dit. Il faut donner des conditions initiales, hein, d'accord. On résout un problème à données initiales, donc il précise ça très clairement. Donc il dépend de x, y, z et du temps, dans des variables spatiales et des coordonnées spatiales et temporelles. Et des conditions, alors ce qui est important, c'est que bien sûr, les équations que Euler avait établies, en fait, elles vivaient un peu dans enfin, pas dans le vide, il n'y avait aucun domaine contenant le fluide. Donc là, dans un vrai fluide, bien sûr, il y a toujours soit des parois, soit des frontières libres. Et sur ces parois ou ces frontières libres, il faut donner des conditions. D'accord ? En particulier, si on veut parler de la théorie des vagues, la frontière horizontale, disons, la frontière du haut du fluide est libre. Il faut donner une condition sur la surface, et c'est l'objet de la remarque qui est ici, des conditions particulières auxquelles la surface, même du fluide, devra être assujettie pendant le mouvement. Alors, donc, quelles conditions on va mettre sur la surface libre ? C'est un point sur lequel je vais insister, parce que c'est quand même un point important pour trouver les équations donc de l'air avec frontière libre, dont là je cite toujours Lagrange. On suppose tacitement dans la théorie du mouvement des fluides que les particules qui sont une fois à la surface du fluide y restent toujours pendant tout le mouvement. Cette condition paraît en effet nécessaire pour que le fluide ne se divise pas, mais forme toujours une masse continue. Cependant, nous verrons qu'il y a des cas où elle ne doit pas avoir lieu. Donc c'est une approximation, là c'est une hypothèse, disons, de modélisation. Quand vous utilisez les vagues, la surface du fluide, on ne peut pas prendre en compte le fait que des particules de fluide peuvent s'échapper. Donc ça, en langage moderne, on dit que la surface est bordante, c'est-à-dire qu'en fait, les particules qui sont à la surface libre y restent. Et ça, on le traduit par une équation que Lagrange écrit, que la dérivée le long de la surface est constante. Hein, c'est la condition de dérivée particulière le long de la surface est constante. Alors, une remarque aussi intéressante, c'est que Lagrange utilise les coordonnées dites eulériennes dans tout le mémoire. Il ne considère jamais les coordonnées dites lagrangiennes. par Euler. Alors, ce qui, bien sûr, personnellement, me gêne pas du tout, mais bon, il y a quand même un inconvénient à utiliser les variables eulériennes, c'est qu'on ne peut pas considérer le cas où la surface n'est pas un graphe, essentiellement, d'accord. Donc, bon, je ne l'ai pas dit, mais peut-être je le dirai plus tard, c'est qu'essentiellement, le cas que traite Lagrange, c'est le cas où la surface est un graphe, hein, d'accord, au-dessus d'un fond, disons. Mais bien sûr, en coordonnées eulériennes, on ne peut faire que ça. En lagrangien, on peut décrire des surfaces qui ne sont pas des graphes, des choses comme ça, par exemple, d'accord, que ne considère pas du tout Lagrange. Mais enfin, bon, c'est déjà ce qui fait déjà suffisamment impressionnant pour pas considérer ce cas. Voilà, donc en fait, il y a aussi des considérations sur lesquelles je vais un petit peu... là, j'insiste un peu sur le côté modélisation, donc qui est tout à fait actuel. Et en fait, on peut donner ce traité à lire à un étudiant, quand on veut modéliser et trouver les équations des vagues, on peut très bien donner le traité de Lagrange, ça comprend très bien, à part les notations qui sont un petit peu exotiques, mais voilà. Donc en fait, on écrit des conditions de surface hein. Bon, y compris les surfaces dans le fond du fluide, par exemple. Et bon, il écrit les équations que je vais réécrire après dans un langage plus contemporain. Je ferai une espèce de digression tout de suite après, vous montrant les équations en langage dans des notations plus habituelles. Mais il y a une remarque extrêmement importante, et je l'ai mise en rouge, c'est à mon avis un des points les plus importants du traité, et c'est vraiment ce point dont on peut dire qu'il a donné lieu, disons, à une grande partie de la théorie, même mathématique, disons, autour des vagues actuellement. Donc, tels sont donc les principes et les formules générales de la théorie des fluides. La difficulté ne consiste que dans leur application. Bon, c'est bien beau d'avoir des équations générales, mais bon, il faut pouvoir en faire quelque chose. Mais cette difficulté est si grande que jusqu'à présent, même dans la solution des questions les plus simples, on s'est contenté d'employer des méthodes particulières et fondées sur des hypothèses très limitées. Pour diminuer autant qu'il est possible cette difficulté, nous allons examiner maintenant comment et dans quel cas les formules générales peuvent être simplifiées. Nous en ferons ensuite l'application au mouvement des fluides dans des vases ou des canaux de figure quelconque. Donc ça, c'est l'idée essentiellement que quand vous avez un système physique très, très compliqué, dont on a assez peu d'espoir, même de nos jours d'ailleurs, de déduire des propriétés qualitatives, on va essayer de trouver des régimes particuliers. Alors, dans le cas de Lagrange, ce sera des régimes d'amplitude, de longueur d'onde, sur lesquels on puisse en quelque sorte zoomer et trouver des modèles simplifiés qui permettront de décrire une dynamique locale dans ce régime. Donc ça, c'est une idée extrêmement moderne et qui est utilisée, je veux dire, par plein de gens maintenant. Et en particulier, donc, dans la partie traitant des canaux de figure quelconque, ça comprend la théorie des vagues. Oui, alors j'ai pas dit, parce que j'ai pas traité tout le mémoire, qui est très riche, donc dans le mémoire en particulier, donc dans les considérations sur les fluides compressibles, ou incompressibles d'ailleurs, il considère les cas où le champ de vitesse dérive d'un potentiel, d'accord, donc des écoulements potentiels. Il s'interroge sur est-ce qu'il peut y avoir des champs de vitesse qui ne découlent pas d'un potentiel, dans des écoulements irrotationnels, et il dit oui, effectivement, on fait des rotations. Donc il donne des exemples concrets d'écoulements irrotationnels. Bon, encore une fois, ici, je parlerai d'abord comme fait Lagrange pour la partie, disons, vague, que des écoulements incompressibles, et aussi, je parlerai aussi, comme aussi fait Lagrange, dans cette partie du mémoire, d'écoulements potentiels dont le champ de vitesse est le gradient d'un potentiel. Alors, je vais juste maintenant donc, faire une petite digression alors ça sera aussi en français, mais la partie moderne sera en anglais. Donc je vais rapidement, pour préciser un peu les choses, écrire un peu en langage, disons, contemporain, donc le problème des vagues. Donc il s'agit de... Bon, là, le domaine est ici. On a un domaine, un écoulement... Alors quand je dis l'écoulement bi- ou tridimensionnel, c'est qu'il y a en fait deux types de variables spatiales. Il y a la variable horizontale, donc qui est notée Z, Bon, j'ai oublié de faire un graphe. Et puis il a noté la variable horizontale qui peut être x, y, donc c'est l'écoulement deux-dimensionnel, dont l'écoulement de l'océan en général est deux-dimensionnel, mais il y a des cas où on peut supposer l'écoulement dans un canal, par exemple, il est monodimensionnel, auquel cas d vaut 1. Donc le domaine du fluide, donc c'est un domaine, alors pour simplifier, j'ai pris le cas où le fond est constant, donc à la hauteur moins h, d'accord. Donc ici, la hauteur moyenne étant z égale 0. Donc ça, c'est l'écoulement du fluide, le domaine du fluide, donc entre cette surface libre, donc en haut et ici le fond. Voilà, que j'appelle ici oméga de t. Donc le champ des vitesses, je distingue les vitesses horizontales et verticales. Donc la vitesse grand V, c'est la vitesse horizontale, et petit w, les vitesses verticales. Donc l'action les forces qui agissent sur le fluide, c'est la gravité, d'accord. Et on a noté ρ, l'intensité du fluide. Et voilà. Alors bon, je traduis un langage moderne, disons ce qu'a écrit Lagrange, mais en fait c'est le même langage que Lagrange. Hein. Le fait que les conditions de frontière, donc elles sont bordantes, hein, ça veut essentiellement qu'il n'y a aucune particule du fluide qui les traverse. Alors quand c'est la surface libre, c'est juste l'équation c'est l'équation qu'avait écrite Lagrange, que j'avais écrite. En général, donc quand j'ai une surface donnée par l'équation sigma égale 0, donc on prend la dérivée matérielle le long de l'écoulement, et c'est l'équation qui est écrite ici. Sigma t plus v gradient sigma égale 0. Et quand on applique ça successivement à la frontière libre, et à la frontière libre, donc c'est les données par grand sigma égale z moins zeta de x et de t. Donc on a l'équation quadrillée de Lagrange, et sur la frontière fixe, donc qui est donnée par le fond, donc c'est z égale moins h, c'est juste que la composante v3, la vitesse est nulle. D'accord. Donc ça, c'est la condition aux limites qu'on obtient. Disons, c'est essentiellement Lagrange. Un peu retraduit dans un langage un peu, je peux fixer les idées. Et ensuite, il y a une équation sur la pression que Lagrange aussi écrit, bien sûr, que je ne vous ai pas mis, mais c'est aussi, en fait, c'est du Lagrange. Hein, donc, en fait, on suppose donc une condition sur la pression. Donc, la pression à l'interface est continue, donc on suppose que la pression en haut est égale à 0, hein, en gros, et on obtient l'équation P égale 0 sur la frontière libre. D'accord, donc ça c'est encore Lagrange. Et le fait ensuite que Lagrange écrit aussi qu'on a un fluide incompressible. J'aurais dû passer d'ailleurs en anglais. OK, so say that the Laplace of phi equals 0, the Laplace equation for phi, which translate the fact that the divergence of v is 0, okay, on the domain. So Lagrange also wrote this condition. So to go a bit further, so you have to use the so-called Bernoulli equation. So to do that, it's very easy that if the flow is potential, so you can write the Euler equations in terms of phi, and you have a gradient. Okay, it's a gradient of something equal 0, so you can integrate. Okay, to get rid of this, and then you get the equation of phi, equation 12, which is a so-called Bernoulli equation, I think. And so we have, of course, f of t will depend only on t, but you can eliminate it by change variable, and you reduce to this equation in red here, which is the equation on the free surface. On the free surface, you have this equation for phi. Okay. But again, in memoir by Lagrange, you have the equivalent of this, of course, with a different notation. And then you have to add the two boundary conditions. So this previous one, just the Euler equation in this setting, and here you have the boundary condition. So the one on the actually it's a z equal minus h the notation. So on the bottom you have dz phi equals 0. So no fluid penetrate the bottom, and the free surface you have the condition written by Lagrange saying that the particle of fluid are just following the free surface. Okay, so it's just Lagrange, nothing more than Lagrange, but maybe just to it's more handy for us to since after that I will go to the modern developments, and I need these notations to follow. Okay, so Yes, okay, so now maybe I'll skip speaking English. So now the point of Lagrange is you have to simplify the equation. So because even in this form, you will see later that this is a variable system. It's very difficult to do mathematics on it. So Lagrange, of course, was aware of that. And what is nice is, he could have just stopped and say, okay, this is hopeless, I will... But he tried to do something. And to do something, you have to simplify the model. And for instance, you, as I told you, if the flow is potential, you have the Laplace equation for potential phi, which is written by Lagrange in this form. And again, il sait, mais cette équation n'étant intégrable en général par aucune des méthodes connues, nous supposerons que l'une des dimensions de la masse fluide est fort petite à l'égard des deux autres, en sorte que les coordonnées Z, par exemple, seront soit très petites vis-à-vis des coordonnées X et Y. So what he's doing, he performs a formal expansion in terms of Z. So taking Z as a small variable, so you get rid of one variable and you get a simpler problem. So at that time, of course, it was very difficult to solve this Laplace equation. So and particularly, what he does, it just expand phi in terms of in power series like this. So I took his notation. So phi prime is the zero term, and phi prime is extra. And I will focus, as I told you, on the part of the mémoire which concerne du mouvement d'un fluide contenu dans un canal peu profond et presque horizontal, et en particulier du mouvement des ondes. So even if you reduce to the potential situation, so even if you expand phi like this, it's still complicated. That's what Lagrange sait. Le calcul intégral des équations aux différences partielles est encore bien éloigné de la perfection nécessaire pour l'intégration d'équations aussi compliquées que celles dont il s'agit, et il ne reste d'autres ressources que de tâcher de simplifier cette équation par quelques limitations. Et, for me, this is really the most impressive part of the memoir, the fact that from this very complicated system is able to derive, of course, formally, something which can be made mathematically rigorous, okay, and we skip some physics. So it's both interesting mathematically, and you still have some physics, as you will see in the next slide. Essentially, what he does, let me say it, so here's the quotation of Lagrange. He is doing two things. First, he's linearizing the system at the free surface, at the trivial solution zero. Okay, but it's not enough, because even as you will see in a moment, even if you do that in the water wave system, you get a non-local equation. Okay, and at that time, what you have to do, basically, you use Fourier transform, okay, to solve it. Okay, so how do you reduce to a PDE? So what he does, essentially, he takes the limit of infinitely long wave. He considers the so-called shallow water regime. So shallow water, I will explain what it means, and he takes the limit of infinite, so it says long wave situation, but you take the limit of infinite long waves. And then you get some PDE, and which has some link, of course, with the previous one, which I will write here. And if you do that, you get something for phi prime. Again, phi prime is just the first term in the expansion of phi in power series of z. And for the equation of phi prime, so you get a closed equation, which is nothing else, still using the notation of Lagrange, which is nothing else that the wave equation, what they call wave equation. What it shows, G is just the gravity, alpha is the depth of the fluid. It's H in my notation. So. And of course, Lagrange remarque that cette équation est entièrement semblable à celle qui détermine les petites excitations de l'air dans la formation du son en ayant égard qu'au mouvement des particules parallèlement à l'horizon. Okay, so he derived from this very complicated system, so the water wave system, which is something rather difficult mathematically, because first it's the non-local system, so it's the solution lives in a varying domain, so it's really so he's able to get this simple equation. So and actually, what is very nice is he does some numerics, some example with that. For instance, he consider so the velocity of the wave, of course, is square root of g alpha is notation. So. And so he gave some numerical, he takes some example. For instance, he considered what you call the pied de Paris. So, pied de Paris should be something like 30 centimeters, more or less 2 centimeters. So he expressed, of course, and then he compute in fact the velocity of the waves, assuming that you have one foot of depth. And so, which is also very interesting, is compute the inverse problem. So, if you know the velocity of the wave, of course you can reconstruct the depth. We have some numerics on that. So, I measure the velocity, and I can reconstruct the depth, which is in the notation and square about this. Okay, so this is something. So. Why it is not so silly physically? I hope it is the next slide. So it's a very simple PD. If you consider it with respect to the full system, it's very simple. But still, it keeps some physics. It keeps some useful fact. For instance, if you can apply it to a tsunami wave, for instance, in the ocean, in the full ocean. Of course, not close to the coast, but in the full ocean. So if you assume that, for instance, you have an ocean of depth about 4 kilometers. So the assumption of the so-called shallow water assumption is kh very very small. So h is the height of the ocean, so 4 kilometers for me, and k what is called the wave number, so just the inverse of the wavelength. And for tsunami in the ocean, the wavelength is huge. It's about 200 kilometers, for instance. So if you compute kh in this situation, it gave 0.02, which is small in some sense. So it fits into the shallow water regime. And if you take the velocity predicted by Lagrange, you find about 700 kilometers per hour, which is the correct order of magnitude for velocity of a tsunami. So it's enough. If you live in the south coast of Java Island, if your tsunami occurs 500 kilometers from your place, you have time to escape, provided the authority give you say you where to go. But on the other hand, the tsunami is 50 kilometers. It's too late, and you are dead before. So it's something which keeps some science. It's not. And this is very impressive. And you will see later that this approach of making a zoom on, so you make a zoom here on very specific dynamic, okay? But you find a model which still keeps some physics. And of course, it's not totally obvious to make this rigorous in the sense of, okay? And again, I will show you how is it possible to do it. But of course, it's only again a part of the memoir by Lagrange. There are no consideration again on say compressible flow, but the part of essentially the part on the waves, on water waves, it's just more or less what I told you about. Just to finish this historical part, so David Land told me that 2 days ago, actually, that Newton has got the same formula for the velocity of the water waves. That's something which I don't know how he did it, but apparently Lagrange was aware of that, and he wasn't. He disagreed with Newton, and this is one part in the memoir also. Cette équation. Cette équation means the wave equation that he was deriving. Okay? So cette équation comprendra donc la théorie générale des petites agitations d'un fluide peu profond. Et par conséquent, so you see the two things. Well, petite agitation means I linearize, okay, and peu profond means I take this shallow water regime. Okay? It's not only linearization; it's something more I mean, deeper than that. Et par conséquent, la vraie théorie des ondes formées par les élévations, les abaissements successifs infiniment petits d'une eau stagnante et contenue dans un canal ou bassin peu profond. La théorie des ondes que Newton a donnée dans la proposition 46 du second livre étant fondée sur la supposition précaire et peu naturelle que les oscillations verticales des ondes soient analogues à celles de l'eau dans un tuyau recourbé, doit être regardée comme absolument insuffisante pour expliquer ce phénomène. Newton didn't, well, of course, at the time Newton, there were no Euler equations, so he was deriving, so maybe you know. But I just learned this 2 days ago, so it's I didn't have time to check in Newton. Okay, now I will make a big jump. So last part is et après actualité du mémoire. Okay, so why this memoir is important and why it's still worth to read it. So I will go back after to the mathematical result connected to the water wave system and to the Euler equation briefly, but I will first make a point on a very important step which was achieved by Zakharov in 68 and again by Craig Sulem in 92. There were two motivations. The first one was that, as I told you before, the water wave equations are set in a non-fixed domain, so it's not very handy to work on this in such a situation for PDE system. So, is it possible to reduce it to a fixed domain, say to R2 or R? Okay. And second, and actually Zakharov did the two at the same time. Is it possible to prove that this system is Hamiltonian? So, does he have a nice structure? And this is what Zakharov did. Actually, he did a lot of things. It was, I think, a thesis, a very short paper. When, so the first really very nice idea is to change a variable. Okay. So instead of considering, say, for instance, the potential phi and the elevation zeta of the wave, so you take as a new variable the trace of the potential on the free surface, okay, that I call psi. So the psi, of course, depends only on x. It doesn't depend anymore on z. So it is a trace of the potential. So the potential, I recall you, it solves the Laplace equation in the domain here. So you have delta phi equals 0 here. And you take the trace, assume that you have this, you know this phi, you take the trace on the boundary, and you call it psi. And it turns out that if you know psi, if you know the trace on the boundary, you can reconstruct phi. So how you do it? So first, you assume that you know the z. You just have to solve the Laplace equation. So you solve delta phi equals 0, phi equals psi on the here, and here it's a Neumann condition, d phi dz equals 0. So you can do it, and you have a phi. And you have this mapping we associate to psi. Of course, this mapping depends on zeta, because, of course, the surface, okay? And you associate or it could be dz phi or dn phi, normal derivative, okay, it's almost the same, at the free surface. And this operator has a name, it's called the Dirichlet-Neumann operator. It has nice, of course, it's linear in psi, but highly nonlinear in zeta. Okay, so the difficulty being that, mathematically, how the solution of elliptic equation depends on the domain. A problem which goes back to Hadamard. So Hadamard has some nice work on this, the dependence of such problem with respect to the domain. So it's not trivial, but actually it turns out that if you use these two variables, everything can be written in terms of psi and zeta. Okay? And here the rest, so you can just forget about the first line. So you get a system which maybe seems a bit ugly, but you have the big advantage of being set on a domain which is Rd, d equal 1 or 2, depending on if you are considering flows in a 2D space or 1D space. And also, which I didn't write it here, but you can express this system in Hamiltonian form. I don't use it here, so I don't want to write it, but it's there are the canonical variable, psi and zeta, with which you can write the Hamiltonian of the system, which is, of course, very, very nice to know that the system is Hamiltonian. This is due also to Zakharov. Okay, so what is the advantage? Also, this is, to me, it's a concept which is very important for two reasons. First, it's mathematically very handy, and also it's very, as you will see later, it's a very easy form to derive asymptotic models, in both formally, say in the spirit of Lagrange, or rigorously in the spirit of modern analysis, which are not the case of your partial Lagrange, when you have to expand everything in Taylor series, you have to assume that everything was analytic. It was not so obvious, but in this formulation, you will see that things will be more easy. So to have just to go back, I will go back to Lagrange, to make the link between this formulation and Lagrange, and there is a link, of course. So the first thing is to linearize this system here. That means you consider only, you linearize at the zero surface. And what you have to do is not totally trivial, because of course you get rid of all the nonlinear term, but it remains one term which is not totally trivial. In the equation for zeta, you have the Dirichlet Neumann operator at the free surface, at the surface zero, which is not a trivial, simple thing, but not totally trivial. It's amounts to solving the Laplace equation in a flat strip. Okay, so you can do it by Fourier. Now you can do it by Fourier transform, and you get here the solution here, and you plug this solution of z of 0 into the equation. You can reduce this system 19 to the equation 20, which is the so-called linearized water wave system. And you see that it's not a PDE, because it's expressed in Fourier in terms of Fourier multiplier. So what I call d bar, it's just minus Laplacian to the power 1/2. So if you write it in Fourier space, the symbol is modulus of xi. Okay, so it's not a local thing. But you see, if you do formally, if you assume that h, or you go in Fourier variable, so here you have a public tangent of h xi. So you know very well, for if xc is small, you can replace a tangent by xc, and you get exactly what Lagrange did. Okay. So first you get the so-called dispersion relation for water wave, which is very important. So you express that the wave are dispersing. So apparently if you have localized initial data, the wave should disperse. Okay. And so here are the relations here, well-known relation. And then if kh is very small, you can approximate the tangent by tangent of x by x, so speaking, and you get exactly the wave equation, which was derived by Laplace with the correct velocity. With the advantage, everything can be very rigorous, because what you have to do, you have to express mathematically in which sense this delta operator approximate a non-local one, and this can be done. Okay, so it's a way to. So it's very fantastic. Lagrange did that almost 2 centuries before this thing. So now I will just show you the what is the actuality of Lagrange with respect to research in water wave theory. First, just briefly, what happened for the Euler equation in a fixed domain, say. So it took a long time to establish a rigorous result. So rigorous, I mean solving the Cauchy problem or something like that, or you fix initial data, and you want to show that at least locally you have a flow, which of course it's not trivial mathematically, but it's trivial physically. It's a kind of Cauchy-Lipschitz theory, if you want. But of course for a PDE, Cauchy-Lipschitz theory is very difficult. So it took a long time. So the first result was by Liechtenstein in the 20s. And you can see also Cato in a different setting. It was in 3 dimensions, local well-positiveness in 3D for the Euler system. Okay, I think it was in the whole space, R3. And in 2 dimensions, there was a property of the flow, which is that the rotational, the curl is transported by the flow. So you can use that to get a global result in 2 dimensions. And this has been done by Udovic, first by Volibner, and under some restriction, and in general case by Jodovich, but not so long time ago. So we established that for the 2D Euler, so in a fixed domain or in R2, say, you have a global flow. But of course, seeing that you have a global flow doesn't say anything about the behavior of the flow. I mean, you know, it's not a qualitative behavior. You have a solution, okay, which is globally defined, but it's not enough if you want to. Okay. Now, if you go back to the water wave system, which of course is more complicated than the Euler system, because you have to deal, even in the potential case, because you have to deal with this free surface problem. So the first result was established in an analytic setting by Shimroth and Kano Nishida, but of course it's not a very nice setting because in analytic, okay, it's not very natural. But the first result in a finite regularity case was established by group of people, Nalinov, Yoshihara, and Craig, under small. It was in one dimension, okay, and for small initial data. And the first really general result concerning the local well-posedness of this water wave system was established very recently by C.J. Wu, but in the infinite depth case. I mean, in my notation, H was infinite, which of course is not, and in the proof it's very crucial. In the proof of Wu, she really used the fact that, she used Clifford algebra into this, something which are not valid in finite depth. And the first general result, general in the sense that you have dimension 1 and 2, the data can be big in some space, and the depth is arbitrary, and the bottom can be not only flat, it can be whatever, was established recently by David Lann. But again, it was a small, it was local theory. So in some sense, it was not enough to describe any type of dynamics. If now you want to go to see what happened for, can we get global solutions? So of course now it's much more difficult. And essentially, there are two types of results. So the first sort of results are very difficult mathematically, but that don't say much about the physics, because essentially they establish that you have global solution for small initial data. Small, I mean physically, you have a notion completely flat. You just perturb it locally, and you have a global solution. Because physically, it's totally tautological. I mean, you know, what can happen if you? But it's very, especially the paper by Lazare and Delors, because technically, Lazare and Delors consider the 1D case, and so dispersion on the wave is get weaker when the dimension is smaller. So in this case, 1D is more difficult than 2D. Okay, but again, it's a result which is nice mathematically, but it doesn't tell anything about some interesting dynamics. So another result which is interesting for the dynamics. It's a long-term existent result, a long-term with respect to some physical parameter. I will explain that in a moment by Alvarez Sayonego and David Lann. So they didn't prove global well-posedness result, but they prove existence for the full water wave system on the time scale which is enough to justify the asymptotic models. Okay? Which of course it's exactly in the spirit of Lagrange, because after all, if you derive, for instance, the wave equation, you want to say, compare the solution of the wave equation with the one of the water wave, but you need to know that the water wave system has a solution at least on the time scale on which the model is a model. Okay, so you need this kind of theorem. And so mathematically, you see, it's a classically, PDE people, again, think about the dichotomy between local or global, which here is not really relevant, because what you want not local or global, but you want long time being exactly what I will explain later, in a time which is long enough to justify the model. It's a different issue, that local versus global or something like that. So now I go back a bit back. Of course, between Lagrange and 20th century, there are a lot of interesting results concerning the asymptotic models. So people trying to go further than Lagrange, in particular to consider regimes which are more general. For instance, Lagrange didn't consider at all the dispersion of the wave. He didn't consider the nonlinear effect. which of course are very important. So so again, so I will just here I explain the thing I told before. So the system is too complicated to have some hope to describe the dynamics for the whole system, okay, except in very simple case like perturbation of zero. So what you have to do is to zoom a different regime, a bit like a dynamical system. You make a normal form to describe locally the dynamics. But here, of course, the regime is not around a fixed point. It's just you fix a regime of wavelengths or amplitude and so on. So for that, you have to first to define small parameters in some sense, and then to try to zoom at this regime and to describe models which will describe the dynamics in this regime. Of course, this idea goes back to Lagrange. After Lagrange, in his memoir, did that for the regime which leads to the wave equation. Okay? So a big step forward was by Boussinesq, who, among others, derived nonlinear models, and he derived in particular the so-called Korteweg-de Vries equation, before Korteweg and de Vries, in a regime which is more general than Lagrange, in the sense that it's a regime which is weakly nonlinear and dispersive. So you take into account the dispersion of the wave and the nonlinearity. And in particular, this model is, again, it's very simple. If you, well, probably all of you know this PD, but if you consider it, it's much, much simpler than the water-wave system, but nevertheless, it still describes some interesting physics. In particular, it can justify the solitary wave, which was observed by Scott Russell in a channel in Scotland, a famous story. So for that, you have to, as I told you, you have to define small parameters. So small means small with respect to what. So you have to define dimensionless variables, and you have to define characteristic quantities. For instance, it's well, if A is the typical amplitude of the wave, so this quantity. If lambda is a typical wavelength of the wave. If h is a typical height of the layer. So you get new variable without dimension, so for zeta, for z, etc. And you define small parameters. So there are many ways to define small parameters. So the classical one, which was used by Boussinesq actually, was to define what they call epsilon, which is the ratio of A on h, amplitude of the h, which measure, if you want, the amplitude effect, the nonlinear effect of the wave. And mu, which is a square of the ratio h over lambda, so the h over the wavelength, with it's called the shallowness parameter. But there is another regime which eventually will lead to a Schrödinger equation, which is called a modulation regime, for which the small parameter is the so-called wave stiffness parameter when you consider the ratio of the amplitude over the wavelength, okay? Which is a very epsilon, which can be expressed of the previous one like this. And in this regime, you will make expansion with respect to this parameter. And this will lead, of course, to different asymptotic models. So, for instance, before showing some models, so if you do that, first I'm considering the regime with epsilon and mu. So you have to rewrite the Zakharov-Sulem system including this parameter. So you have the same system as previously with a bunch of small, these parameters epsilon and mu. And what you have to do mathematically, if you want to derive model from this, you just have to expand this non-local operator z of mu and epsilon with respect to a small parameter. And this can be done by PDE techniques. It's just a question of elliptic. Basically, you're solving a linear elliptic PDE with non-constant coefficient in the domain, and you want to understand how the solution depends on the domain. Okay? So you can derive with respect to this is a shape derivative with respect to the domain. So there are a lot of techniques which allow you to do it. Okay, and you can even do it formally using MATLAB, and you will get formula. But so you can do it formally and rigorously in the sense you can justify rigorously which was not possible with the approach of used by Lagrange when you use the original equation. So, for instance, for the regime, the so-called Boussinesq regime, so you get the so-called Korteweg-de Vries equation, which is written here, question 23. So, in this KdV equation, you reduce to d equal 1, and you force the wave to go in one direction. So, you kill the wave going to the left, say, and you get this equation here. So, epsilon is small, so what you have to, at order 1, you have the wave equation, so dt plus dx applied to u, it's a transport equation, wave going to the right with 81. Everything at this scale, of course, 1 is... and then you have correction of the epsilon, which include both the nonlinear term and the dispersive term. And of course, you neglect terms which are order epsilon minus square. If you do another regime, so this is the so-called weakly Boussinesq regime, so well, epsilon and mu are small. If you consider mu very small, mu is a measure of the dispersion effect, and epsilon order 1 means you consider the nonlinear regime, so you get the so-called Saint-Benoît system for shallow water system for which is this system, which is purely nonlinear, okay? Which is nonlinear. We don't have any dispersion, and again, you can go further. If you want to go further, you have to add new terms, which are order mu. Okay. So, but again, this is, and of course, there are many other systems. So let me just write another one. If you define the so-called stiffness parameter, this one is considered by Lagrange. So you get the Schrödinger equation with a different sign here. It's not a misprint, it's just a minus here. It's a way to relate Schrödinger and the waves, and Lagrange is not a priori obvious. So here, what is psi? Psi is a complex envelope, so you consider the slowly varying envelope of a oscillating wave. So psi, if you take real part of psi, you will get the envelope of this wave, and it satisfies this PDE. And this was again derived by Zakharov in the same paper when he derived. His paper was 5 pages long, but he has at the same time the new formulation, the Hamiltonian, and the derivation. Of course, it was concise. Now, I will just conclude that since I am a mathematician, so I want to try to explain what do we need to do if we want to justify the model. Justify, I mean mathematically. Okay? First, the first thing you have to do, you have a model, so obtained by one way or the other. So the first notion is the notion of consistency. So consistency is a notion which is not at all dynamical. It's just a static, say, algebraic condition. What you have to do, you assume you have a solution of the water wave system given by defined on a time 0t. You plug it into your synthetic model and you make an error. But of course, there will be no dynamics in this. It's a bit like for people in numerics, if you know the finite difference scheme, so approximating a PDE, so the scheme has to be consistent with the equation, but consistency is not enough to be convergent. It's just purely algebraic. Okay? Of course, here it's more complicated, but everything can be done in terms of this Dirichlet-Neumann operator, basically. For instance, I gave you 2 examples in the Boussinesq regime, which will lead eventually to the KdV equation. What you prove that you can approximate the Dirichlet-Neumann operator by epsilon delta plus a thing you can control, and you can make this rigorous. And in a regime of leading to Saint-Benoît system, you approximate so the small parameter here is mu. There is no small parameter here because it's a nonlinear regime. You just approximate z of mu of zeta by minus mu 1 plus zeta times Laplace of psi. But again, this can be done perfectly rigorously. So this step can be done formally, okay, or rigorously, and it's not too complicated. It could be technical, but not too complicated. But again, it's not enough. If you do that, you have not proven that. So what you have to do, there are 3 important steps. First, say, for instance, if you consider this first formula for z, so it's supposed to describe the dynamics on time scale of order 1 over epsilon. Okay? But to have some relevance, you have first to know that the full water wave system has solution on time scale of at least order 1 over epsilon. Okay? And this step is very difficult, and this step was connected to the paper of David Lann and Alvarez Samaniego I was talking before. This is what I told you as a long-term existence for the full system. This is one step which is difficult. Then you have a second step, you have your synthetic model. you have to prove that the solution lives long enough to be comparable to the one of the water wave system. So this is very easy for the Korteweg de Vries because it's globally defined, but it's not so easy for systems. Okay? So again, it's a PDE question which concerns the long-term existence of solution of a PDE, of a system of PDE, with respect to some parameter. Okay? And the third step, of course, is to prove with an error estimate that the solution of the model are close to the one of the Euler system. Okay? And this is still the object of intensive research, and because there are many different regimes, and there are the models are more complicated. So I just show you maybe the more simple one. So it's far from being complete, but there are some regimes for which everything is complete. For instance, for the Boussinesq regime, which include in particular the KdV equation. So this theory is complete, so everything is known. So it exists a long time for the water wave system, on long time for the Boussinesq system, which are the two-way propagation version of the KdV equation, and the error estimate, which is proven to be order epsilon square t, which is optimal because when you derive KdV of Boussinesq system, you make an error, which is you neglect terms which are order epsilon square. Okay? So you cannot be better than this. So for this regime, everything is complete. Of course, it's also complete for the regime of Lagrange, but it's much easier because Lagrange is just a linear thing. Okay, so well, it was just so the talk was just the main aim of the talk was just to show you that this Lagrange memoir is really important in the maybe not because it derived the system, which I mean probably many people at that time could do, but the way they have the idea of you have to try to simplify in a rational way the full system to get something which will describe the dynamics. So if you want to know more, so there are two excellent books. So one by Olivier de Régol, which concern the history of fluid mechanics from Bernoulli to Prandtl. So Prandtl is 1930, like that. Prandtl is a boundary layer. So everything is explained much more. And for the mathematics of the water waves, emphasizing the model aspect, I mean the fact that you want to approximate the water wave system by models. You have the recent book of David Lann, where they describe not all but many of the classical regime, and it is state of the art what is known on this on the water wave system in connection with this consideration. Okay, so I think I will stop here.